Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start. So last week we went through this Rothschild-Skills theorem that says if you have some pure risk, which means the expectation of this risk conditional on x equal to 0, then that's something you wouldn't like. right? So especially the utility, the expected utility of this y tilde is less than expected utility under this x tilde. So we show that or prove that through mainly two things. One is the Jensen's inequality we use here, right? And then if you take the expectation on both sides of this expression, then you can get the expression simply through this law of iterated expectations. So hopefully in your tutorial, the tutor actually told you a little bit more about law of expected expectations, right? So, so now let's try to use this with a sort of very simple applications. So you have n of lotteries, right? So each have some payoff, which is random. So it's x1 tilde, x2 tilde to xn tilde. All right, so they are independent and identically distributed. That's what we call the RID. And then you want to choose the weight alpha, so alpha 1 to alpha n, such that, of course, the sum of alpha equal to 1, right? And then you want the combination that gives you the best payoff, basically. All right, so one sort of your obvious guess is to just have a complete diversification. So if you just choose alpha I equals to 1 over n, so it's equally distributed for all the n's, then the payoff will be this 1 over n to the sum, 1 over n times the sum of all the xi tildes. All right, so this is, let's call this z tilde. So we want to show this z tilde is actually optimal. All right, so let me actually summarize what we're trying to do. Right, we want to try to do the simple diversification, which is just 1 over n, is the best solution for IID distributed random lotteries. Okay, that's what we are trying to do. So let's say you have some distribution, alpha 1 to alpha n, that is not 1 over n. Okay, so it's anything other than just equally distributed. Okay? Then the total payoff, which is just sum of your alpha I times x tilde I, can be written as z tilde, which is the sum of equally weighted lottery payoffs plus this sum of ai minus 1 over n xi tilde. So why ai minus 1 over n? Because here in z tilde, you have 1 over n of x tilde. Right? So this is just like you add 1 over n and then minus a 1 over n of xi tilde, but the add 1 over n xi tilde part summation is just z tilde. Right, so in other words, this is, if our alpha I choices is not 1 over n, we can always see it as a combination of 1 over n and the difference in weight of your alpha I and 1 over n, the payoff, sum of the payoffs, right? So this sum of ai minus 1 over n xi, this is just some random variable, and we want to show if the expectation of this equal to 0 or not. Right, if expectation of this epsilon tilde equal to 0, then we can just use the Rothschild-Stiglitz theorem that says this is not optimal. Right? We don't want something that's pure risk, but has higher variance. Right, so in particular, we know this epsilon tilde, that's sum of ai minus 1 over n xi tilde. If I take the expectations, all right, so expected epsilon tilde condition on z, that can be written as sum of ai minus 1 over n, so that's just directly from above, expectation of x tilde condition on z. So I can pull this part, ai minus 1 over n, outside of this expectation because these are all known numbers. These are not stochastic variables. Okay? So all we need to do is to just show this is equal to 0. Okay? So we know that the conditional expectation must be some identical number, right? So this conditional expectation itself just is some identical number, right? Let's say this is k. Okay? Now, if this is the fixed number k, let's look at this part. What is this part? If you ignore the expected x tilde I condition on z, this part should equal to 0, right? This is very obvious, right? Because sum of ai minus 1 over n, that's equal to sum of ai minus sum of 1 over n. Okay? So sum of ai equal to 1, sum of 1 over n equal to 1 also. Okay? So as long as this is a fixed number, then we can take this fixed number out of the summations. Right? We can just look at this part, and this part equal to 0. 0 times any fixed number, that's 0. Okay? So we show that this conditional expectation of epsilon tilde condition on z, that's just 0. So it's 0. That means this epsilon tilde is just pure noise. Right? If it's pure noise, then it's less preferred. Right? So z tilde is preferred to all the other allocations. Because we said at the start, alpha I is any other combination of the weights. Right? So we know that as long as your allocation is not 1 over n, it will always be less preferable than 1 over n. Okay? So we show that under IID conditions, the equally weighted portfolio actually give you the best payoff. Okay? But one thing I need to call your attention to is you have an important assumption. This is IID, the independent identically distributed. Okay, so that's why we can do, took all these things out of summation, things like that. So that's the first application we have. Now let's see something really, really simple, right? So let's say you have a game, and this game have two outcomes. It's either $1 or $3 with equal probabilities. Right? Now suppose whenever the outcome is 3, I will add $1 with the probability of half. Okay? Now let G be the distribution of this compounded lotteries. Right? It's very clear you would prefer G. You don't really need to think about this, right? Because from the original half and a half of $1 and $3, now if it's $3, I get some extra probability of half to get $1 extra. Right? Of course, I like this chance because I'm losing nothing. Okay? So what does that mean? That means if I define the two CDF, so this fx, that's the original CDF, right? So it's from 0.5 to 1. When 0.5, it's when it's between 1 and 3. when it's reach 1, when it's greater or equal to 3. So that's my original fx. Now I have additional probability. Whenever it hits 3, I'll have an additional probability of half chance of getting 3, half chance of getting 4. All right? So half a chance of getting 3, half of the half, that's 0.25, plus original 0.5, that's 0.75. I can get 3, another 0.25, I can get 4. All right? So if I just plot these two CDFs, right, very obviously which one you will choose. All right? Which one you will choose? You will choose lottery G. All right, so this is what we talked about. This CDF of lottery G is underneath the CDF of lottery F. Okay, so this exactly is the first order stochastic dominance we talked about. Right, if you calculate expectation, it's very obvious. Lottery G will have a higher expectation. Okay? Now let's change the game a little bit. Let's say now, whenever the outcome is $3, I'll either add $1 or subtract $1 with half-half probability. Right? Now, which one actually would you prefer? So that means whenever the outcome is 3, the actual outcome will be either 2 or 4, right? With half-half probability. So in terms of expectations, these two games have the same expectation, right? Now, same expectation, but the outcome is more spread. So this is a mean preserving spread. Okay? Which one would you choose? Lottery F or lottery G? Well, it's the typical risk aversion, right? We have increasing utility function but concave. So which one would you pick? As long as you're risk averse, you pick which one? F. Right? Because F has the same expectation as G, but the outcome of F is more spread. Outcome F is either 1 or 2 or 4. Outcome of G is either 1 or 3. Okay? Well, what I can do is to just plot this new CDF. This is the new G, right? So new G is either 1 or 2 or 4. Probability as before. Now if I just plot these two functions, it's very obvious the CDF of F is underneath CDF of G initially. Then you have single crossing. Okay, remember in the lecture notes we have like normally distributed functions. It looks really good, have these two crossings. But here you also have the single crossings, just from this blue line, just go from underneath to go up. Right, so this is really just our second order stochastic dominance. Right, and it actually makes sense because, as we said, it has the same mean, but it's more spread. Okay? So either from the function itself or from the graph you plot or from all the other definitions, you get to the conclusion you should prefer this blue line, which is the original F. All right, so this is a very simple example to show you what the first order stochastic dominance is, what the second order stochastic dominance is. And this second order stochastic dominance is very often associated with mean preserving spread, which satisfies the Stiglitz theorem we talked about at the beginning. Okay, so log normal we talked about before. What I want to talk about next is how to sort of do a typical maximization problem to solve for your optimal allocation in the risky assets. Okay, so this will use some of our knowledge to do the maximization and some of our knowledge to use the log linear properties. All right, so let's say we have what you want to maximize expected utility, and expected utility is exponential form, which is CARA, the constant absolute risk aversion. Right? But some of you will say, well, if I remember correctly, I don't know if you remember correctly, my CARA exponential utility function is 1 minus e to the power of minus a of w or a of c. Remember that? If you look at your lecture notes, right? The function I give you is 1 over e to the power of minus something. Right? But why I don't have 1 minus here? Why I just have this minus e to the power of something? Okay, that could be an answer. When we take the derivatives, the 1 goes away. But more fundamentally, when we try to maximize the utility, any linear transformation, positive transformation doesn't matter. Right? Because we only care about the shape of utility or ordering of the utility, not the numbers. So I can just sort of run away, do this maximization, subject to my budget constraint. So this is my called budget constraint because this is the dynamics of my wealth depending on the return of the portfolios, right? So my wealth next period, W of t plus 1, that's equals to my original wealth, WT, times my gross return, right? Which is 1 plus the return of the portfolio. Easy enough? That's how my wealth will change. So I know my portfolio return, that's just equal to my alpha of the risky asset return plus 1 minus alpha of the risk-free return, right? Then I can simply write it as risk-free return plus alpha t times the risk premium. Okay? So you can verify it by yourself. Try to do it at least once by yourself. So how do we do this maximization? Should we just take the derivatives, use the Lagrangian? Well, one thing is kind of clear because we know this WT should be equal when we hit the maximization because we want to have the utility as high as possible, right? So one thing is we can just plug in this WT into this maximization problems, right? If we do the derivatives, I mean, of course, we can do the derivatives, but the problem is we have expectation of some exponential function. That's a little bit difficult to do in terms of just taking the derivatives, right? But what I can do is take the logs of it first. So if I take the log of this maximization function, again, log is a positive transformation. It doesn't matter. It doesn't really change our maximization problem, right? So if I take the log of, if I just take the log of this expectation of minus e to the power of minus AW, so remember this is log normal. So log of expectation equals to what? Log of expectation equals to expectation of the log plus half of the variance. Come here. Log of expectation equal to expectation of the log plus half the variance of log x. Okay? So, if I take the log, this becomes negative, it's still there, right? And then expectation of the log. So log of this e to the power of minus aw, that's just a minus a over the w, t plus 1. Okay? Plus the half of variance. Half of variance, this is a half. Variance, I need to calculate a little bit. What is the variance of minus of the aw? Well, because it's variance, the coefficient needs to be squared, right? So that's a square of the variance of wt plus 1. So what's the variance of wt plus 1? Well, we know that wt plus 1 equals to the risk-free plus alpha times the risk premium times this wt, right? So the variance of wt plus 1 only depends on my alpha and the variance of rt plus 1, right? Because the risk-free doesn't have variance, okay? So if I take the variance of that, that's just alpha square sigma square. Everyone see this? If you're getting lost here, it'll be really difficult for you in the future. Okay? Because this is, like the basic building steps of the models, right? So you should know where this variance of this future wealth coming from. The variance of future wealth is coming from the variance of the returns, right? And the variance of returns depend on the share that's investing in the risky assets, right? And because this is variance, whatever share I have should have square, because all the coefficient gets squared when you calculate the variance. Okay? So the variance equals to a square alpha square sigma square. Now we can do is instead of maximizing expected minus e to the power of aw, t plus 1, I can just maximize awt minus t plus 1 minus half of a square alpha square sigma square. That's the same thing. Right? So we transform the maximization into the log form. And now let's plug in this wt plus 1 into this maximization. So wt plus 1, that's just my risk-free return plus alpha times the risk premium, and everything else is just followed. Copy from the above. All right? Now I can take derivative with respect to what? Alpha, because we are choosing alpha, right? We're trying to choose alpha to maximize it. So if I take a derivative with respect to alpha, so the only thing that's have a coefficient before alpha is this term and this term, right? So for this term, I have A, it's still there, that's the coefficient before, A times RT minus 1 minus FT plus 1, that's the risk premium part, and I have WT, that's the coefficient before alpha T. The coefficient on the second term is half canceled out, right? So it becomes A square sigma square times alpha. Okay, so that's our first order condition. Well, I can write it because this is the minus equal to 0, so I just change the terms. That's the equation, right? Once you get this first order condition, well, it's simple algebra. You can solve for alpha. Okay? So let's look at this alpha for a little bit. What is this alpha? Does it recall anything for you? Do you see anything similar like this? What? Something in the lecture notes is very similar, almost exactly the same as this. In lecture notes, I call it theta. What is it? Yeah, so what do we call that? When you have really small risk, right? What's the optimal allocation to the risky assets? Remember that in the lecture notes? In the lecture notes, we go through this operation by, assume there's a K units of the risk, things like that, right? And then you derive this optimal allocation will be the risk-free rate on the top, the risk premium on the top, right? Or expected return on the top. I think in the lecture notes it's expected return on the top, right? And then in the bottom you have risk aversion and the variance. Remember that? Right. So here it's very similar. You have the expected risk premium on the top, and then this is just your initial wealth itself. Then you have risk aversion A on the bottom and the variance of the risky assets sigma square on the bottom. All right? So in fact, this is something really general. Right? Risky asset equals to risk premium divided by your risk aversion times the return variance. All right, so if you sort of go to an investment bank, you're doing some sort of investment advising. A lot of times they advise their customer, if you ask them, how much should I put in the stock and how much should I put in treasury? They will recommend, maybe you should put 60% in the stock and 40% in the risk-free assets like treasuries. Where do they get this number? They get this number from here. The risk premium, as we talked about in the US, is about 6%, right? A typical risk aversion is like 2 to 3. Let's assume it's 3. The variance, annual return variance of the S&P 500 is about 0.18 standard deviation, so it's 0.18 square. Right? So if you calculate this gives you some answer as 60%. That's where it comes from. Right? So this is sort of, remember what we do is, here the title says, myopic optimization. Why they call it myopic? Because this is just one period. Okay? Assuming you are doing it one period. You have T to T plus 1. It's not a multiple period. Right? It's not like dynamic optimization. It's myopic optimization. But let's say each period the return distribution is IID, right? Then remember, if it's IID, cross-sectionally it's equally weighted, right? But if it's IID over the period, that means all the period risky weight will be the same. So if it's IID return, this can be extended to longer horizons. Now, let me ask this question. Assume, again, you are this investment advisor, and this is end of 2008, beginning of 2009, right? And your customer come to you and ask you, oh, you know, my stock has been losing money for such about like 20 or 30%. What should I do? Should I sell the shares? Or keep the share? Or something? Well, then you recall in your investment class, someone told you this formula, right? And you say, oh, risk premium, I don't really know, right? Maybe it's higher, maybe it's lower. Looks like it's lower, but I'm not sure about the future. Risk aversion doesn't really change, I assume. Return variance, wow, that's much higher now, right? And then you will get to the conclusion the share of the risky asset should decrease. So if the share of risky assets should decrease, then you should advise your customer to sell his shares. What's the problem with this advice? Well, think about assumptions. What assumption do we need? Return needs to be RID if you can use this formula forever, right? So in the financial crisis, is the return RID? Well, if you go to Yahoo Finance, look at the returns, it's hitting the bottom at the beginning of 2009. Which means as soon as you advise your customer, returns start to go up, right? So obviously at the sort of height of financial crisis, your return will not be RID, which means you cannot just use this same formula to advise your customer, right? So I think that's kind of the benefit of some advancing starting the advanced class, right? You may not know the mathematics behind it. You may not, know how to derive things, but at least you should know where things are coming from under what conditions. So that when you use those formulas and the things, knowledges, whoever teach you, you know the limit of these things. Okay? For example, you know CAPM, but you should know sometimes CAPM doesn't work. Okay? All right, so I think that was the tutorial 2. This week we talked about SDF, right? So SDF is something sort of very abstract. It's kind of hard to get a concrete example on. So what I thought is to give you an example of how the SDF comes to work. With some just log normal distributions. All right, so if we assume log of consumption is growing at some z, okay? And then this z is normally distributed, right? So the consumption growth is log normal distributed, okay? Now you have utility function of this power function, right? We can calculate M, which we call SDF, very easily. If you recall from the lecture notes, that's beta of U prime CT plus 1 divided by U prime CT. That's beta of this C1 over C0 to the power of minus gamma. But C1 over C0, that's just the growth rate, right? So if we take the log, we'll have the log growth rate. So if we take the log, we have the log beta minus gamma of z, or m equals to beta of e to the power of minus gamma c. That's our SDF, right? So you'll say, oh, what is the SDF? Remember, z is normally distributed, right? So e to the power of negative gamma z will also be log normally distributed, right? So it's a random variable that has log normal distributions, okay? So M, the SDF itself, is random, okay? So in particular, this log normal have, if you take the logs, it has the mean of log beta minus gamma mu, and the variance is gamma square sigma square. All right, you can just see it from here. Well, if you don't believe me, you can ask the computer. Now the computers can even do the derivative for you. You don't really need to know this, but I just show you if you specify your utility function, if you specify your u prime as the differentiation of utility function with respect to c, and then your c1 is c0 times exponential of z, and then your SDF formula you plug in, then ask for what is the m, you get this, which is exactly as when we do it ourselves. Right, so this is the same as this, what the computer gives us with derivatives. So with this, we can look at the risk-free rate. The risk-free rate, by definition, should be equal to 1 over expected m. Right, so how do we calculate expected m? Well, m is the log normal, right? Log m distributed normally, so expected m, I can just use the log normal property. Right, so that equals to e to the power of this log beta. So this is the log beta minus gamma mu. That's the mean from here, right? So mean plus half the variance. Variance is gamma square sigma square. That's the variance, right? So e to the power of mean plus half of the variance, so the half of the gamma square sigma square. That's expected m. Right, so if I just simplify it a little bit, this RF is just 1 over expected m, so that would be 1 over beta. What's left is e to the power of, because it's 1 over, so it's because negative becomes a positive, so this is positive, gamma mu minus half of gamma square sigma square. Okay? Then you can further simplify, expressed as log of the IF, you have this expression. Right? That's the basis of intellectual notes when we use it for data. Right, so I can ask the computer to compute again. Now let's use some data. I get this data from World Bank data site, right? I get this household final consumption expenditure. If I look at Australia, United States, consumption growth rate is like 3% annually. The standard deviation is about 0.018. That's the volatility of the consumption. Right, so remember this formula. Go back here. We have log of IF equals to this plus gamma mu. So we already find the mu. Half of gamma square sigma square. We also find the sigma, right? And then assume some normal gamma. We can solve for what the log IF is. All right, so this is just, I assume gamma equals 2, mu equal to 3%, what we see from the data, sigma equals to 0.018, and then just plug in the formula for log IF. I get, well, log IF equals to about 6.7%. Well, which is way too high, right? Okay, in your normal life, risk-free rate is like 1% on average, right? Or a little bit above 1. So this is, what is this code? It has a name for this, right? Some puzzle. What's this called? That was on Monday. Remember risk-free rate puzzle? Right, so if we assume some gamma, the risk-free rate is much higher than what we observe. The risk-free rate we got from the model is much higher than what we observe in the data. All right? But that's the risk-free rate puzzle. Now we can move on to the risky asset. So we can calculate the equity price also. What's the equity price? Equity price, P equal to expected MX, remember, right? That's our general formula. So let's suppose this X is the payoff from dividend, and the payoff from dividend is correlated with your consumption. Okay, so this rho actually may be higher than 1 because you only take a proportion from your dividend payment for consumption, right? So that's the setup. Then we can calculate, because this is log D, then D is just the exponential of the growth rate is rho times Z, basically, right? So that's the growth rate, rho times Z. And then I can calculate the price equal to expected M of X, M times X. X is D1 now. So I just plug in this D1 into this, right? And I know M. M we calculated before. M is beta times e to the power of minus gamma Z. That's my SDF. Right, so I can collect the terms for the exponential term, and that's what we have. Right, so I collect the exponential term given it's a log normal. Remember the log normal expectation, right? So that's what we have for the price. So we can solve for price. Equity price. What is equity return? Equity return, gross return is just what you get next period divided by what you pay out, right? What you get is D1. What you pay out is P. Right? So D1 minus P, that will be your return of equity. Or you can express it into log return, seems to be sort of easier to recognize. And then I can take the expectation of this log return, again using my log formula, log expectation formula, so that I can calculate the expected log risk premium. So the log risk premium seem to be half of 2 times rho gamma minus rho square of sigma square. So then I can plug this into our parameter again. Rho, if gamma equal to 2, rho equal to 1, assume rho equal to 1, sigma equal to, again, 0.018. The risk premium we calculate, it's really small. Right, so again, this is a risk premium puzzle. Right, if we want to make this number big, we have to make this gamma big, unrealistically big. Right, so that's, again, we show the risk premium puzzle. We can also show the risk neutral probability. What is the risk neutral probability? Remember in the formula we have in class, right? Risk neutral probability is your SDF M divided by expected of M times the original probability pi. So we solved for M, solved for expected M before. All we need to do is to just plug them in, right? And do a little bit of simplification. And this pi, we know, is the distribution of normal CDF, right? So we know this pi star is this expression. If you look at this expression, this is Z minus mu minus gamma sigma square, right? If you compare this expression to expression on the top, the only difference is instead of mu here, you have mu minus gamma sigma square here, okay? So this is the CDF of the normal distribution when the mean is not mu, mean is mu minus gamma sigma square. okay, the variance is the same. So the risk mutual probability is just have the normal distribution, have the mean shifted to mu minus gamma sigma square,